Hello! Today we are going to be talking about improper integrals. Although the name is suggestive of some ghastly breach of decorum, I think you will like these. There are various forms of improper integrals, but the most common type is when we have an integral of some function, a definite integral, that runs not as x goes from 1 to, say, 10, or 22, or 5 million, or even 5 million millions. Any of those are perfectly proper integrals. What would make it an improper integral is if this upper boundary of integration were infinity. Ooh, very improper indeed. Positively scandalous. No, not really scandalous. It's very easy to make sense of something like this if we think about it in the usual calculus way of dealing with infinity, which is to sneak up on infinity with a limit. But before we even get to that, let's just take a minute to get a feel for what this thing even means. We've got some function that we're integrating. There's nothing special about this function except that I'm using it to make a point that will come later on, but any function in theory would do. And we are integrating from 1 to infinity. Well, we know that any integral, any definite integral, is a weighted sum of infinitesimals. We chop the region of integration into infinitesimal bits, attach a weight to each one, call in our friend the integration daemon from earlier videos, who then adds up all the weighted infinitesimals in his little book. And the total he reaches at the end is the value of the integral. So that hasn't changed. But the region of integration is of a different sort than we're used to. We're used to integrating over a finite interval. We start here and we stop here. And the integration daemon comes along, chop, 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 add, and then he's done. Well, there doesn't seem to be an end to his task now, because the region over which he is integrating on the real number line, sure, it begins here at 1, but then it just goes on and on and on and on and never stops. It goes all the way to infinity. So we would have to imagine cracking this infinite interval into little infinitesimal bits all the way down. And at every real number x in our domain of integration, the integration daemon stops there, or rather at an infinitesimal neighborhood of that point, whose length is an infinitesimal dx. He multiplies that infinitesimal length dx by the value of this function at that value of x. That's the weight he attaches to the infinitesimal, and their product is precisely this stuff right here. And he does that at every one of these infinitesimal little bits, giving us infinitely many of these things. One for each value of x is the intuitive idea. And then the daemon adds them all up, which is what the integral does. It's a sum of all those weighted infinitesimals. And when he totals everything up in his little book, that should be the value of the integral. So the basic intuitive meaning has not changed. But the question is, how can he do that when there's no stopping place? Usually we say start at 1 and stop at, 22 or whatever. If we say start at 1 and just go forever, how does he manage to add everything up at the end? Can he even do that? Won't he just end up with a sum that is infinity itself and therefore useless to us? Well, sometimes that does happen, and sometimes it does not. And it will be important for us to be able to decide when an improper integral makes sense, or as we will say, converges to some finite value, and when it does not make sense, when it either just blows up to infinity or behaves in an even stranger manner, but at any rate does not converge to a finite value. When that happens, we say that our improper integral diverges. The miracle, in some sense, is that certain improper integrals converge, despite telling our integration daemon to add all the way to infinity. We sometimes end up with a sum that is finite. And this integral that I have chosen for you here is one of those cases. It will be a convergent improper integral. And I want to explain to you why that is so before we actually discuss how we would go about computing its value. Okay, so I claim that this improper integral converges, that it's equal to some finite number. I want to show you why that is so intuitively. And to do that, I'm going to make use of some geometry and something you learned all the way back in elementary school. So let's start with the geometry. We know that integrals can be understood in terms of area. So let's try to interpret this in terms of area. I want to start by thinking about the graph of this function. Well, that's pretty easy. I mean, 3 over 10 to the x could be rewritten as 3 times 10 to the minus x. Well, the 3 is just going to be a kind kind of stretch factor of the core function y equals 10 to the minus x. And that's just exponential decay. So something like this. It's going to cross the vertical axis. Well, let's see. When x is 0, y is going to be 3, and then it dies off very rapidly because as x grows, the denominator gets huge while the numerator just stays at 3. So this graph never actually touches the x-axis, but it is approaching it asymptotically. So anyway, if I am integrating this function from 1 to infinity, the idea is I'm starting where x equals 1 and going on forever. So this integral could be thought of as the area under the curve from 1 to infinity. And it's very natural for someone to say, okay, this integral represents that area, but that area goes on forever. So isn't that area infinity, which means that this integral should be infinity? In other words, the integration demon ends up with a sum of infinity. Isn't that right? Isn't this what did you call it? A divergent improper integral? What's the big deal? Well, the big deal is that that isn't what happens, somewhat counter to our intuition. It turns out that even though this area is unbounded, it's not like we can draw a giant circle that contains it all. No circle will contain it all. Even though that area is unbounded, it actually remains finite because it's narrowing so rapidly that the whole thing stays finite, even though it's unbounded. And you might say, finite, but it's unbounded? I don't buy it. Well, that's okay. You're free to say that. You should say that. You should demand an explanation, and I'm here to supply it. I hope that after another minute or so, you will all agree that this actually makes perfect sense. So let's think about this curve, and let's think about this area. Let me mark a few points on this curve. The point directly above x equals 1, of course, is going to be 1/3. I've just popped 1 in for x. And now if I go here where x is 2, and I go up to the curve again, that point's coordinates will be 2 and 3/10 squared. In other words, 3/100. Now do the same thing above 3 and 4 and 5 and 6 and imagine it all the way out to infinity. All right, so far so straightforward, but where am I going with this? Well, what I want to do next is draw some rectangles in here. Not infinitesimal rectangles, just ordinary rectangles, like this. Each one of these rectangles has a width of 1 unit, and the heights of the successive rectangles, well, those are just the y-coordinates of those points we were just talking about a moment ago. Notice that the area under the curve, the integral that we're looking at, is definitely smaller than the area contained in all of those rectangles, if we're imagining those rectangles continuing out to infinity as well. So in other words, I could say that this integral, which is that area under the curve, is certainly less than the area of all those blue rectangles. But what do I know about the area of those blue rectangles? That's something I can work with because everybody knows how to find the area of a rectangle. You multiply the height times the width. So I can actually get an expression for that area. That's going to be, well, what's the area of the first rectangle? Its width is 1 and its height is 3/10. So that first rectangle has area 3/10. How about the second rectangle? Well, its width is 1 and its height is 3/100. So its area is their product, which is 3/100. Well, what about the third rectangle? You get the idea, 3/1000. Well, the fourth rectangle has area 3/10,000, and so on and so forth, and this pattern continues forever. What do I know about this sum? Well, rewrite it as a decimal. This is where we're going back to elementary school, like I promised. 3/10. Well, that's 0.3. 3/100. Well, that's 0.03. 3/1000. Well, that is 0.003. And so on and so forth until the cows come home to infinity. But what's this sum? Well, of course, if you put 0.3 and 0.03 together, you get 0.33. And then this tacks on another 3, 0.333. And this tacks on another one, 0.3333. And so on and so forth. 3's without end. But what did you learn in elementary school? What's 0.3333333 repeated forever? Well, that is 1/3, of course. All right, so what have we just learned? We have just learned that this improper integral is equal to something that is less than 1/3. That means that this improper integral converges to some finite value. The value of this integral is not equal to 1/3. This integral is less than 1/3. But the fact that it is less than 1/3 is enough to tell us that it is finite, that this integral converges to some number. We will find that number exactly next, but this explains why I gave you this weird function for our first example, because I could convince you, with a little help from your elementary school teacher, that the very idea of an improper integral converging makes sense. Okay, now that you're convinced that it can make sense to have an improper integral that converges to some finite value, let's talk about how to actually compute it. And don't worry, you don't have to go through an argument like that every time you see an improper integral. I just wanted to do that once to develop your intuition as to why such a thing makes sense. All right, how do we compute it? Well, as I hinted earlier, the calculus way of dealing with infinity is to sneak up on it using a limit. Because you might say, well, look, I don't know how to compute this integral from 1 to infinity, but I know how to compute it from 1 to 10, or 1 to a million, or 1 to a billion, or 1 to a trillion. Those are all fine. And this is where the idea of a limit should be occurring to you. Because if I compute this integral from, say, 1 to a trillion, so I'm getting all the area under the curve between 1 and a trillion, that's a pretty good approximation to the full integral out to infinity. But I don't want an approximation. I want it to be exact. When we think about this in the calculus way, we cut to the chase. Why don't we just integrate from 1 to, just put some symbol there, 1 to k, where I'm just thinking of k as some huge number, and then take the limit as k goes to infinity. So this will be beyond 1 to a trillion, beyond 1 to a trillion, trillions. We're passing through all those things, 1 to k, and take a limit as k goes to infinity. Well, if you understand that much, you're basically done. That equal sign right there is the key to the whole idea of an improper integral. To integrate from some finite value to infinity, we just integrate from that finite value to some other finite value, and then take a limit of the whole thing as that new value we have interposed there goes to infinity. And we claimed earlier that we could integrate this function from any finite value to any finite value. So let's put our money where our mouth is, integrate this, let the limit just hang out here in the wings, and at the end, when we're done with this, we'll take the limit and we'll be done with the whole thing, and we'll have the exact value of our original improper integral. Okay, so first let me bring the limit along for the ride. I think this is going to be easier if we rewrite this function as 3 times 10 to the minus x. Let me go ahead and pull this constant 3 through the integral, like so. In fact, constant multiples can be pulled through limits as well, but let's just leave it there for now. Okay, now I'm just trying to integrate an exponential function. We can come up with that just by using our good old guess and adjust technique. Let's see, what's that antiderivative going to be? It's an exponential function, and their derivatives are very close to themselves, so I might initially think, well, let's see, is it going to be 10 to the minus x? Is that the antiderivative? Well, clearly not, but it should be close. It should get us a toehold here, because if I took the derivative of just that, what would I get? You remember how it works. The derivative of an exponential function is almost the function itself, but then I also have to multiply by the logarithm of the base. And in fact, in this case, I have to do the chain rule, because it's not 10 to the x, it's 10 to the minus x, so I would pick up a negative as well. Well, that's pretty close to the function I was aiming at. It's only off by a constant multiple. So you know what I'm going to do. We'll just put minus 1 over log 10 in there as a constant factor. That way, when I take the derivative of this whole thing, that piece just sits there and cancels with that stuff, and I'm left with 10 to the minus x, the function I am aiming at. Okay, good. I have my antiderivative. Oh, and of course, for my bracket notation, I need to bring the boundaries of integration over, which are 1 and k, that finite value. Great. Let me pull this constant through the brackets, and in fact, then I will pull all the constants through the limit as well. So I end up with all this stuff. Well, let's go ahead and do that evaluation. So in place of all that bracketed stuff, I get 10 to the minus k minus 10 to the minus 1. And I think the next step will be even easier to see if I rewrite these negative exponents like so. Now, let's actually take the limit now that I've got this into such a simple form. What happens in the limit there? Well, as k goes to infinity, what happens to 1 over 10 to the k? Well, the denominator gets huge. So 1 over something huge is something tiny. And in the limit, this term goes to 0. And of course, the 1/10 just sits there. It is not affected by the limit because it is not written in terms of k. Oops, and I just realized I forgot to bring my negative down. Okay, fix that. Well, when I do this arithmetic, I end up with 3 over 10 log 10. And that value is equal to our improper integral. So now we have it. We have computed our first improper integral. This improper integral converges to the value 3 over 10 times log 10, which, in case you are interested, is about 0.13. So yes, less than a third, as we said. And that is the idea of an improper integral in a nutshell. I do need to show you some variations on this theme and give you some hints of applications where this sort of thing can arise. But if you understand what I have done so far, you understand the idea. And again, everything really comes down to this one step of replacing an integral that goes to infinity as one of its boundaries of integration with an integral that goes to some finite value, and then we take a limit as that upper boundary goes to infinity. Okay, let me show you a second example. This will be the integral of the reciprocal function, 1 over x, from 5 to infinity. If you want to think about that geometrically, we could think of it as corresponding to the area under the curve, y equals 1 over x, as x ranges from 5 to infinity. Is that finite, like the last example we had? Or will it be infinite? Well, let's find out. We know what this means, so let's jump straight to it. Instead of integrating this function from 5 to infinity, let's integrate it from 5 to some other finite value. Let's call it t for the sake of variety. It doesn't matter what we call it. The important thing is that I'm integrating the function from 5 to t, wherever that may be, but then I am taking the limit of all that stuff as t goes to infinity. Again, this equal sign is where all the action is. All the intellectual action, anyway. The rest is just computation. But let's do it. Of course, we keep the limit waiting in the wings till its big moment on stage arrives at the end. Now we're integrating 1 over x, the reciprocal function. Well, everybody knows an antiderivative of that. It's going to be log of x. And you might say, wait, it's log of absolute value of x. Well, that's true, but all the x's we're dealing with are positive, so I don't need the absolute value. But I do need to adorn my bracket notation with this 5 and this t. And now evaluating that stuff, I get log of t minus log of 5, and that is the expression whose limit I want as t goes to infinity. Well, what happens to the logarithm as its argument goes to infinity? It goes to infinity very, very, very slowly, but the logarithm does grow to infinity. You, of course, remember what the graph of the logarithm looks like. I'm sorry to insult your intelligence by mentioning that here, but I have to do it, not for you, but for someone else in your class. Anyway, it looks like this. It goes to infinity, but it takes its time. If you ever forgot what it looked like, of course, just remember, the logarithm function is the inverse of the exponential function, and everybody knows what the graph of the exponential function looks like, even that person who sits behind you in class, who is probably the one who forgot what the logarithm function looks like, which means that he can always figure it out by taking the exponential function's graph and reflecting it over the line y equals x, because that's how any function and its inverse function have their graphs related. Anyway, I mentioned this all just to remind you that as t goes to infinity, log of t goes to infinity. So this first term is blowing up to infinity. Blowing up maybe is the wrong term. Slowly creeping towards infinity. Meanwhile, log 5 just sits there. So this whole expression goes to infinity, which means that the limit here is infinite. And that means, thanks to our connection of equal signs here, that our original improper integral diverges. This is a divergent improper integral. It does not converge to some finite value. There's not much we can do with it. Or to phrase it geometrically, this area is infinite. It might look kind of like the area of the region we were looking at in our first example, but it's different, very different. Okay, let's look at another example. And immediately after doing that one, I want to show you a shortcut that I think you will appreciate. Let's integrate 1 over x squared from 1 to infinity. Let's see, is this one going to converge like our first example or diverge like our second? Well, to find out, let's turn this into a limit. We're going to take our integral, and instead of going from 1 to infinity, we'll go from 1 to, let's use c this time. So we will be integrating our function from 1 to the constant c, and then we will take the limit of that integral as c goes to infinity. Well, that's an easy integral. It'll be even easier to see if we rewrite 1 over x squared as the power function x to the minus 2. When we do that integral, well, let's see. It's a power function, as we said, so we jack up the exponent by 1, which brings it to minus 1, and divide by the new exponent. So divide by minus 1, which is the same as multiplying by minus 1. And of course, I have to carry over all my stuff onto the bracket notation. In fact, let's pull this constant minus 1 through the bracket like so. And then when I evaluate this bracket notation, I get c to the minus 1, which is 1 over c, and 1 to the minus 1, which is 1 over 1, better known as 1. I guess we could clean this up a little bit by distributing the negative, and then it would become 1 minus 1 over c. Now that's a nice form. So let's go go ahead and take the limit as c goes to infinity. When c goes to infinity, the constant 1 just sits there. 1 over c vanishes. That is, this term goes to 0, so we are left with 1 as the value of our improper integral. So this one does in fact converge to the finite value 1. You're getting the hang of this, aren't you? Sure you are. That means you're in a position where you will appreciate a little shortcut. Let's redo this same integral, but using a little shortcut technique that most people end up using in practice for many improper integrals. Okay, so let me go ahead and rewrite the integrand in that form that we found it easier to work with as a power function. Now, rather than going ahead and writing this as the limit of an integral as the variable runs from 1 to c or k or t or whatever I want to call it, let me just go ahead and find the antiderivative. Well, the antiderivative is easy. It's a power function. As we said, we raise the exponent by 1, divide by the new exponent, which is minus 1, so that gives us a minus here. Go ahead, put my brackets down, and put 1 and infinity right there on my bracket. And let me clean this up by pulling the factor of minus 1 out and rewriting the x to the minus 1 as 1 over x. And let's just keep going with it. Evaluate the bracket notation at infinity and 1. Pop infinity into the function, and you get 1 over infinity. Well, what does that mean? I hear you cry. That is where you have to just bear in mind that even though I can't truly stick infinity into a function, if I just remember that what I'm actually doing is thinking about the limit of this function as x goes to infinity, then I can just proceed normally. So putting infinity into the function, in other words, taking the limit of this function as x goes to infinity, we get, of course, 0. And then putting 1 into the function gives us, of course, 1. And when I clean this mess up, I get positive 1, which is the value of our integral, just as we found in the first version. Isn't that nice? You're still taking a limit, of course, at this stage when we substitute the infinity in, which means take a limit as the variable goes to infinity. So feel free to use this shortcut when doing improper integrals, but never forget what is actually going on under the hood. And if you ever find yourself in a situation where something doesn't seem to quite make sense, just take a step back, express everything in terms of limits, and that may bring some clarity to whatever you are doing. But most of the time we can use that shortcut very nicely. For example, in that previous example where we integrated 1 over x from 5 to infinity, we could have said, okay, well, that's just log of x as the antiderivative. Now what happens here? I pop infinity in for x, so to speak. What's log of infinity? Well, that means the limit of the logarithm as x goes to infinity. Well, that obviously is infinity minus log of 5, which is hopelessly finite, so this turns out to be infinity. So this integral diverges just like we said it would. Bear in mind that in other circumstances, you could end up with some kind of indeterminate form like infinity minus infinity, or infinity over infinity, or 0 over 0. And in those circumstances, you might find it more helpful to go back and put everything in terms of limits. Okay, but how might improper integrals arise in practice? Or is this just one of these math for math's sake type things that will delight some people and leave others feeling cold? No, these things really do arise in practice quite frequently. So I want to give you some examples of how that might happen. Let's take our first example from the world of probability. Even if you have never studied probability or statistics, I'm sure you are familiar with the notion of the bell curve, or the normal distribution, or the Gaussian distribution. These are all names for a family of probability distributions governed by bell-shaped curves of this form. And naturally, there will be some function, I'll just call it f for now, whose graph this curve is. The formula for the function will take different forms depending on where the center of the bell is and how fat the bell is. But those details don't need to concern us here. The important point is that these sorts of functions can model all sorts of phenomena. A standard example would be almost any biological feature where there's a typical value, and then some animals or people, whatever species we're talking about, have lower values and others have higher values, and the further away we get from that mean value, the less and less likely they are to occur. For example, the heights of American men are centered around 70 inches. That's 5'10". And if you go out a little ways each direction, I've marked off 3 inches, which for those in the know is roughly 1 standard deviation here, you end up taking in the majority of the stuff under the bell. And in fact, whatever that area is the probability that a randomly chosen American man will have a height between 67 and 73 inches. So since probabilities correspond to areas like this, and areas correspond to integrals, we can find probabilities with integrals. So we could find the probability that a randomly chosen American man is between 67 inches and 73 inches simply by integrating that function f from 67 to 73. Again, the details of precisely what this function looks like aren't important to us now. All I want you to understand is the connection between probability and area, and therefore between probability and integrals. And if you understand that much, you can see how improper integrals can arise very naturally. Because suppose we were to ask for the probability that a randomly chosen American man is over 72 inches tall. That's 6 feet tall. Well, here's 72 inches on our picture. This area, which in turn corresponds to the integral of the function out to infinity. So from this very natural question, what's the probability that a randomly chosen American man is over 6 feet tall, we end up with an improper integral. And while the bell curve is probably the best known probability distribution, it's far from the only one. Another type of probability distribution is the so-called exponential distribution, whose graph looks like this. It starts at some particular value on the positive y-axis and then comes down and is asymptotic with the x-axis. The general form for such an exponential distribution looks something like this: lambda times e raised to the power of minus lambda times x, where lambda is just some constant that will depend on the particular nature of the thing that we're modeling. Perhaps the most common use of the exponential distribution is to model waiting times. For example, in place of these lambdas, let's put 0.2s. And this function might be a decent model for, let's say, the length of time between the arrivals of successive taxicabs on some street in New York City at a certain time of day. Again, the details need not concern us. Let's just take it for granted here that this is a reasonable probability model for that scenario. Well, suppose you arrive on that street corner in New York City in the given time period just as you see a taxicab pulling away, and you need to get somewhere quickly. And so you might ask, what's the probability that we must wait more than 10 minutes for the next cab? Well, it's a probability. It's going to correspond to an area, namely this area, which of course is an integral. The integral of this function, the exponential distribution, from 10 to infinity. So again, we get an improper integral that will lead us to answer a very straightforward question. This integral is simple enough that let's just go ahead and do it. We'll begin by pulling that 0.2 out of the integral. And now this integral is easy to do. This is just an old guess and adjust type integral. The antiderivative is going to be kind of like e to the minus 0.2x. But of course, if we take the derivative of this thing, we don't get that back because we get a minus 0.2 as well. So to balance that out, I'm going to need to divide by minus 0.2. And now I've got my antiderivative. Bring the boundaries over to my bracket notation. And let's see, let's pull this constant stuff through the bracket. And that looks a little nicer. And now let's go ahead and evaluate. When we pop infinity into that, we remember that means taking a limit as x goes to infinity. Well, as x goes to infinity, 0.2x, of course, goes to infinity. So minus 0.2x goes to negative infinity. And when you raise e to negative infinity, in other words, take the limit of e to the x as x goes to minus infinity, of course, you get 0. Then when we pop 10 in for x, well, we just get plain old e to the minus 2. Simplifying that, we get e to the minus 2 as our integral. And if you run that through your calculator, you will see that it is about 0.135. So the probability that we'll have to wait more than 10 minutes for the next cab is about 13.5%, in the neighborhood of 1 in 8 chance. All right, well, I think you've seen how improper integrals can arise in probability. Next, let's take a look at how they might arise in physics. Now, if you have not studied physics, that is okay. You should still be able to follow the basic idea of this example, which is all that matters. This isn't a physics class, after all. I just want you to see another way in which improper integrals arise in other settings and not just for their own sake. Anyway, I want to give you an example that involves the physical notion of work. Work is bound up with the idea of transference of energy. When we do work on an object by applying a force to it, which then changes the object's position, we are actually transferring some of our own energy to that object. A simple example would be pushing a shopping cart down the aisle in a grocery store. We apply a force to the cart, which is thereby endowed with some kinetic energy, since it is now moving. Another example would be lifting the shopping cart in a heroic feat of strength above our heads. By lifting it up off the ground against the force of gravity, and then just standing there grinning while confused onlookers back away from this obviously crazy person, we have done some work on the shopping cart. And even though it is not in motion like it was over here, we have endowed the cart with potential energy, since if we let go, that thing is coming straight back down. Anyway, work is computed very simply, provided the force involved is constant. In that case, the work is going to be the magnitude of that constant force times the distance the object moves in the direction of that force while the force is being applied. But for this formula to work, the force must be constant. Okay, now let's think about a specific case. This one. How much work is this guy doing on the shopping cart when he lifts it over his head? Well, work is force times distance, and the distance is clear. That's just whatever distance he lifts it, expressed in the appropriate units. But what about the force? He's not shoving the shopping cart up into the air so it leaves his hand and flies up for a ways. He's just applying enough force to counterbalance the force of gravity that is pulling the shopping cart down towards the center of the earth. And what is the magnitude of that force that he has to match? Well, that, of course, is the weight of the shopping cart itself. And provided we are near the surface of the earth, and of course he is, since he's standing on the earth and only lifting it 6 feet or so, provided that condition is met, that force, the weight of that object, is given by a very simple formula. It's the mass of the object times the constant acceleration due to gravity of any object near the surface of the earth. So if the mass of the cart we call little m, maybe I'll put a subscript cart on there, the mass of the cart, we have to multiply that by what we usually call little g. Whether it's for gravity or Galileo, take your pick. That's the famous constant that's about 9.8 meters per second per second. But anyway, that would be the force, while d would be the distance traveled by the cart. So this full expression right here, that product, would be the work that the man does on the shopping cart. So far, so simple. And that would work regardless of whether he's just hoisting the thing over his head 6 feet or carrying it up 3 flights of stairs. Either way, he's just fighting against the force of gravity as it is felt by objects near the surface of the earth. But, suppose he dreams of doing more than that. Not just lifting the cart 6 feet or 60 feet or 600 feet, or even throwing it somehow 6,000 feet in the air. No, our little Hercules dreams of doing so much work on the shopping cart that he is able to fire it off the surface of the earth so far that it escapes the earth's gravitational field entirely. Well, then the question is, how much work would he have to do on the cart to accomplish that absurd feat? And you might say, well, that's easy. How far is it to the edge of the earth's gravitational field? That would be the distance. And then you just multiply by the constant force, which is this thing, right? Well, no, there are 2 problems there. First, there's no clear boundary between where the earth exerts a gravitational attraction and where it does not. In fact, strictly speaking, any 2 objects in the universe attract each other gravitationally. Perhaps very, 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 very weakly, but the force does exist. So you could say that there's no boundary at all. And then second, after a while, we are no longer near the surface of the earth, so we can't use this simple formula for the weight of the object. After all, the further away we get from the center of the earth, the less and less the object weighs, until we are in interstellar space, where it is effectively weightless, and there's basically no force of gravity to overcome. So given those 2 facts, how do we compute work? The force is no longer constant, and the distance is unclear in some sense. Well, this is where you have to put your calculus goggles on, and they will help you see your way to the answer. Sure, the force is not constant. It requires a lot more force to overcome gravity near the surface of the earth than it does many miles above the surface of the earth. But if we think locally on an infinitesimal scale as we move the cart from any one position to another one infinitesimally close to it, this drawing obviously is not to scale, then within that little infinitesimal distance, the force is constant because the weight of the shopping cart isn't changing over that scale. So it's not hard for me to compute the work required to push the shopping cart from any given point to another point infinitesimally close to it. So if I could figure out an expression that gives me the work required to push the shopping cart up just an infinitesimal bit, that's easy because the force is constant there, then I can break the full distance, whatever that is going to be, into infinitesimal bits, use my expression for work on a typical one, integrate it, and I will get the total amount of work. So let's start there. I'm going to need to introduce a little notation. Let's call the radius of Earth capital R, and let's let the distance from the center of the Earth to any typical position of the cart be x. I'm going to do that because when we can no longer rely on this little formula for the magnitude of the gravitational force near the surface of the Earth, and we have to rely on the full-blown formula due to Newton, then we think of the two objects that are involved, in this case the Earth and the shopping cart, as point masses, as if all their mass were concentrated in their center of mass in a single point. That point for the Earth will be the center of the Earth, which is why I will measure distances from there rather than from the surface of the Earth. As for the shopping cart, it is so small relative to the Earth that I don't really need to take its dimensions into account. But anyway, the work required to lift the cart an infinitesimal bit higher from some position x is something we can compute with our basic work equals force times distance formula because the force required is constant there. The cart's weight is not changing over that infinitesimal distance. It is effectively constant. And what will it be? We can't use that m times g formula anymore because this distance x might be very far from the surface of the Earth. So we have to use Newton's law of universal gravitation, which tells us how any two objects in the universe attract one another gravitationally. And that force, as I think most of you will know, is going to be this interesting expression. It's a fraction, and upstairs we have the products of the two masses. I'll use capital M for the mass of the Earth and little m for the mass of the cart. I need some more room here too. That's better. Downstairs, I get the square of the distance between the objects. Well, the object is x units away from the center of the Earth, so that square distance will just be x squared. But I'm not done. That force is not just the product of the masses divided by the square of the distance. The force is proportional to that stuff, and the constant of proportionality is generally denoted capital G. That is just a physical constant built into the fabric of the universe. Now, this stuff is the constant force that we have to apply to the cart to move it from x to just a little bit infinitesimally further out than x. So to move it a distance of dx, an infinitesimal bit of x. Excellent. We've made a lot of progress. Now we have the work required to lift the cart an infinitesimal bit along its journey. And that holds for any value of x. So if we want to push this thing very far away indeed, we have to add up all these little bits of work to get the total amount of work. So we're going to take things of this form and add them up, integrate them as x runs from, well, where to where? Well, the lower boundary is clear. We're starting on the surface of the Earth, which is capital R units from the center. So we're going to start when x is capital R. And we're going to stop when, well, when what? When we reach the edge of the gravitational field of the Earth, you might say. Well, but there is no edge. Ooh, so what do? You know what we do. We integrate to infinity. And now you have seen how an improper integral can arise in a physical context. Oh, but let's not stop here. This is an easy integral, so let's do it. So now we have an expression for the total amount of work required to lift the cart beyond the gravitational field of Earth. Oh, and by the way, you might say, yeah, but that doesn't make any sense. We don't really have to take it infinitely far away. I mean, eventually we do get to the point where the gravitational field is negligible, and that's not at an infinite distance. And you are right, of course. But think about the integrand here. It is vanishing the further away we go because the top just sits there. It's a constant. The bottom is x squared. That's getting very big very fast, so this whole thing is disappearing, which means that the further and further we go out, the closer and closer to zero our function is getting. So since we have no clear stopping place in mind, we might as well integrate out to infinity, since our function is vanishing anyway. Sometimes it's easier to deal with infinity than it is to try to say, well, let's just integrate to some gigantic but unclear finite number, because someone might say, well, why don't you go a little further? Or why don't you go a little less far than that? Well, it doesn't matter. Go to infinity. The extra stuff you're picking up, those weighted infinitesimals at the end, once you get sufficiently far out, really aren't even contributing anything to the whole sum. But anyway, back to our integral. We have an expression for the total work. This is how we do end up defining it. The stuff upstairs, as we said, is a constant, so let's pull that through the integral to get this. Well, that's a really easy integral, of course. It might help to think of it as the power function, x to the minus 2. When we integrate, the antiderivative is minus x to the minus 1, or the negative of the reciprocal function, and evaluating our bracket notation, we get this stuff. Those negatives cancel out, and simplifying it, it becomes big M times little m times big G over big R. And that is the total amount of work that would be required to push the shopping cart from the surface of the Earth beyond the gravitational attraction of Earth. If we do that much work to the shopping cart pushing against gravity, it will be out there in space and it will not come down. One last point I want to make about this. As I mentioned at the beginning, work is about the transference of energy. So let's say that our stick figure man said, oh, what if I can just impart this much work to the shopping cart all at once? Just like fire it out of a catapult or launch it like a rocket. Can I do that? And if I do that, the shopping cart will go up, 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 and never come down. How fast would I need to launch the thing to accomplish that? In other words, what would the escape velocity be for that shopping cart? Well, we can compute that very quickly, because the idea is we would need to put this amount of work into the shopping cart, which was at rest. So if we're just launching it from the surface of the Earth, we need to endow it with this much kinetic energy. And if you've had physics, you know the basic formula for kinetic energy, 1/2 mv squared. So we would need 1/2 mv squared, the kinetic energy of that object, the shopping cart, at the moment it's launched from our giant catapult or rocket launcher or whatever it is. We would need that to be equal to this other quantity, big M, little m, big G over big R, the total amount of work required to push the cart beyond the Earth's gravitational field. But hey, look at this equation. There's something interesting in it. There's a little m factor on both sides. We cancel those out. We can solve for v. That is the velocity of the cart on launch. And if we do that, well, that's easy. We just have to multiply both sides by 2 to clear out that half, like so. Let me go ahead and get rid of those little m's. That's better. And now, of course, just take square roots of both sides to get v is the square root of 2 big M big G over big R. That is the initial velocity we would have to give the shopping cart to shoot it out into space so that it does not come back down to Earth. That is going to be the escape velocity from Earth. Very interestingly, it does not depend on little m, the mass of the shopping cart. So this would also be the escape velocity from Earth if we launched a baseball straight out, or a spaceship, or a boulder, or whatever. And this is just a constant, because big M is the mass of Earth. That doesn't change. Big G is that gravitational constant, that universal gravitational constant that holds throughout the universe. And big R is just the radius of Earth. That doesn't change either. And these are all values you can look up. They're just known constants. And if you put them in the appropriate units, we end up with an escape velocity of approximately 7 miles per second. Now that's fast. Incidentally, when NASA or SpaceX actually does launch a rocket beyond the Earth's gravitational pull, that's not how they do it. They don't just fire it 7 miles per second initially. Good luck accomplishing that. They actually do it in stages, where as the rocket gets higher, it has different boosters that impart more energy to it at different heights as the gravitational attraction of Earth is getting smaller. But I will leave it to your physics and astronomy classes to go into details on that. Here, I just wanted you to see one more example of how improper integrals can arise in settings other than a calculus class where I say, here are some integrals, do them. I promise you, go far enough into any field that uses calculus, and you will encounter improper integrals. Okay, enough of physics. I should mention a couple of other things about improper integrals. They exist in forms other than integrating a function from a constant to infinity. One obvious one is you could integrate a function from -infinity to a constant. The adjustment is pretty obvious there, and there's a homework problem or two in the book where you'll play with that. In fact, you can also integrate from -infinity to infinity, and that is very common in probability distributions like the bell curve we talked about before. If this function is the probability density function for a normal distribution, or for any probability distribution in fact, integrating it from -infinity to infinity gives you the total area under the curve, which is the total probability, the probability that something happens. Well, that, of course, is 100%, or as we would say in probability, it is probability 1. Probability, in a calculus-based context, part of the definition of a continuous probability density function is that when you integrate it from -infinity to infinity, you get 1. But there is one other kind of improper integral that is a little less obvious. Sometimes you can integrate between some finite number and some other finite number, and nonetheless you have an improper integral. What? What on earth? How can that happen? Oh, it's not that hard to see. I'll show you an example. Basically, it means you're running into a vertical asymptote in the graph. For example, let's integrate this function, 1 over the square root of the quantity 1 minus x from 0 to 1. Now there's a problem here. When x is 1, this function isn't even defined because we would be dividing by 0. In fact, let's think about the graph of that function so we can see visually what happens. Let's see, do you know how to graph the integrand? Sure you do. Very rapidly, let's do that down here in the dungeon. I don't know the graph of that off the top of my head, but I know that if I can graph a function, it's pretty easy to graph its reciprocal. So can I graph y equals the square root of 1 minus x? Well, let's see. This is very close to the square root of x, and I know how to graph that. So let's see, can I get to this function from the square root of x by a few simple transformations? Let's see. Oh, I know. First, if I substitute minus x for x, y equals square root of x becomes y equals square root of minus x. Then if I substitute x minus 1 for x, square root of minus x becomes square root of minus the quantity x minus 1. And when we distribute that negative, minus x minus 1 becomes 1 minus x. Okay, good. So I did it in 2 steps, and now I should be able to come up with that graph very easily. Everybody knows the graph of the square root function. Then, when I substitute minus x for x, what does that do to the graph? Well, you should know that. That just flips the graph over the vertical axis, like this. Then, when I substitute x minus 1 for x, which will get me the form I want, what does that do? Well, you should know that too. Substituting x minus 1 for x shifts the graph over by 1 unit, so it'll look something like this. Oh, good, but I don't actually want this function. I want the reciprocal of that function. Let me clear out some of the clutter. That's better. Anyway, I want the reciprocal of this function. What happens when I do that? Well, instead of these things being the y values, it's the reciprocal of those things being the y values. So I just have to take the y coordinates of all the points on this green graph and take their reciprocals, and then I'll have the graph of this function. Well, over here near 1, what happens? Well, there the y coordinates are approaching 0, so their reciprocals must be going to infinity. And over here, where the y coordinates are going to infinity, albeit very slowly, the reciprocals must therefore be going to 0. And therefore, I have a quick sketch of the graph of my integrand. And now I see the problem. Now I see why this is an improper integral. If I try to integrate this function from 0 to 1, I'm looking for this red area right here. And that region is infinite in extent, but going up rather than going right. How do I deal with that? Exactly as you would expect. Let's be very formal, since this is the first one like this we're meeting. We would obviously have no problem integrating this function from, say, 0 to k, where k could be any value less than 1. That's a perfectly normal integral, so we could take that and then take the limit as k approaches 1 from the left, and the rest is just pounding out the details. I should be able to just think of an antiderivative of that. After all, this function is 1 minus x to the minus 1/2 power, so I expect the antiderivative should be something like maybe 1 minus x to the positive 1/2 divided by the new exponent, which is a half. So dividing by a half would give me 2. And then I have to think, since I'm doing a little guess and adjust here, is that the correct antiderivative? Not quite, because if I took the derivative of all that stuff, the half comes down and cancels with the 2, that's good. And then I'd get 1 minus x to the minus a half, but I've got to deal with the chain rule, so I'm going to pick up an extra negative. So this is not quite what I'm aiming at. I need a extra negative factor in there, so I will just supply that, get rid of my scratch work, which nobody wants to see, pop these two values onto my bracket notation, carry the limit down, just let him wait in the wings for now. Oh, and actually, come to think of it, let's take that constant factor of a minus 2 and pass it through the limit, like so. Now I'll bring the rest down, like that. I find it more intuitive to write the radical there when I'm just evaluating. I don't know why. Bring that limit down again, evaluated k, which gives us square root of 1 minus k. Evaluated 0, which gives us 1. Now let's take that limit. As k approaches 1 from the left, 1 minus k approaches 0, so this stuff right here, the square root of 1 minus k, goes to 0. The minus 1 just sits there, so that limit is equal to minus 1, and when we multiply that with the minus 2 that we pulled out a while back, we get 2 for our value of that improper integral. So even though this area goes on forever, it narrows fast enough that the total area is finite. And that's that. This video has gone on long enough. Let's call it a day, go do some homework problems, and I will see you next time when we will complete the chapter by talking about Riemann sums. Until then, goodbye, good night, good day, and all that other good stuff.